Fibers have been in the service of humanity since Genesis. Certainly, if it was the tree of knowledge that got Adam and Eve kicked out of paradise, it was the stuff of trees that would serve them best in suburbia. The first mark of civilization was the adoption of the modesty leaf, a naturally occurring fibrous polymer. In time, other fibrous polymers, such as cotton, were used for fashion shows and other cultural events. The fibrous material of plants is cellulose, the most abundant carbon compound in the world. Cellulose is a macromolecule composed of up to 14,000 glucose units, linked to form an unbranched polymer. A single plant fiber is composed of many cellulose molecules, twisted together in rope-like bundles. To understand how these chains are held together, we need to look at the structure of glucose. Each glucose unit, or monomer, is a carbon ring structure with protruding hydroxyl groups. For simplicity, we'll ignore all but the specific oxygen that links the glucose unit to the chain. What then keeps these long-chained molecules in bundles? The answer is hydrogen bonding between the hydroxyl groups. Hydrogen bonding might be described as a love triangle of one hydrogen atom caught between two electronegative oxygens. The hydrogen is teamed to one of the oxygens in a covalent bond. But the electronegative oxygen is reluctant to share bonding electrons. So, the hydrogen is attracted to the lone pair electrons of a nearby oxygen, forming a weak hydrogen bond compared to the covalent bond. Yet, it is the cumulative effect of thousands of hydrogen bonds that draw the molecules together. And it is the millions of these cellulose chains that give a single fiber its tensile strength. When these fibers are twisted into rope, it has the strength to move armies and remove cities. Sometimes. It wasn't until mid-19th century that chemists began to seriously tinker with natural fibers. Using cellulose as the main ingredient, they allowed it to react with caustic soda and carbon disulfide. The mixture was again reacted with caustic soda. A viscous cellulose complex resulted, which could be extruded through spinnerets into a neutralizing acid bath. Resembling a ray of light, the filaments were patented under the name rayon by the end of the century. Though rayon yarns could be turned into attractive fabrics, they weren't terribly durable. The year is now 1939, the scene of the New York World's Fair. The public has its first glimpse of a revolutionary synthetic fiber, nylon. Still, nature had furnished the prototype in the form of the protein molecule. Nylon, like protein, is a polyamide. It is a long chain molecule whose segments are held together by amide functional groups. A functional group is that part of the molecule which undergoes chemical reaction. The amide functional group consists of a carbonyl from one segment bonded to a nitrogen from another segment. Together, they act like belt buckles, holding the segments together. The amide is formed by allowing a carboxylic acid and an amine to react. The byproduct is water. Now, if an amide molecule has reactive sites at both ends, it can further react to form a polyamide. We've simplified the molecule by illustrating only the amide bonds. It is this head-to-tail structure which fashions the polyamide molecules. What distinguishes different polyamides is what exists between the amide groups. In the case of nylon 6, 6 carbon monomers are strung together to form the polyamide. The polyamides, in turn, are held together by hydrogen bonds. Again, it is the presence of oxygen and nitrogen that promotes hydrogen bonding and gives nylon its tensile strength. Well, almost. A little fine-tuning is required before selling to the textile mills. In the manufacture of nylon, the monofilaments are extruded through spinnerets and twisted on a convergence wheel to form yarn. The yarn is then drawn and stretched to 4 times its original length. Before the yarn was processed through the drawer, the nylon chains were arranged in a loose manner. Stretching thereby aligns the molecules so that the hydrogen bonding between them is maximized. This physical manipulation gives nylon its characteristic flexibility and strength. Most of the time. But when it comes to brute strength needed for today's industries, it is carbon-carbon fibers used to reinforce metals that holds great promise for the future. Very pure synthetic yarns are woven into 3-dimensional arrays. The array is then impregnated with molten plastic or metal. And the composite in a nitrogen atmosphere is carbonized by heating to temperatures in the 650 to 1100 degree range. Impregnation and carbonization cycles are repeated several times, during which heat and pressure are cranked up. This causes the fibrous lattice to restructure into sheets of fused benzene rings, namely graphite. The incredible strength is provided by 3 factors. The extensive network of covalently bonded carbons, the double bonds within the benzene rings, and the metal or plastic which makes up the composite. Once graphitized, the preformed composite undergoes final machining. Today, the aerospace industry is the prime customer for this composite. And so it was that polymers which served us in exile will suit us up as we prepare to leave this earthly paradise.